So, the second lecture is single step methods for initial value problems. Okay. So, we have learnt formally what is an initial value problem. So, now we would like to learn single step methods which are numerical methods to solve initial value problems. So, let us consider an IVP as follows: y dash equals to f of x y, y of x 0 is y 0. Okay. So, now we would like to define a single step method. Single step method. So, what is this? Basically, the numerical methods are the algorithms. In some sense, they are the algorithms to get values at discrete points. Okay. So, your single step method looks like this. We have input and we get output. So, what is the input we are giving? yn prime and the step size, then we get yn plus 1. So, now what is the reason why are we calling this a single step method? So, let us define the process. So, then we will understand y of x n plus 1 equals f of x n, okay, yn prime h and y of x n equals some yn, n equals to 0, 1, okay, say some n h minus 1. So, why are we calling this is a single step method? If you see carefully, there are two indices n plus 1 and n involved. So, the right hand side expects values at point n and left hand side we are obtaining at n plus 1. That means, the process is demanding only one passed value, only one passed value, that means at x n, then it is generating y of x n plus 1. Okay. So, this is the motivation to say that this process is a single step method. Okay. Why it is single step? Now, you can correlate y of n plus 1 is in terms of some y of n. So, only one passed value is required. So, therefore, it is a single step method. Okay. So, example, say yn plus 1 is yn plus, okay, x n h. Suppose there is a method like this. So, this is a single step method because it is asking only x n and y n, it is generating y n plus 1. Suppose say 2 y n minus 3 y n prime. So, this is also a single step method because it is asking only information at one passed value, that is at x n. So, y n is y of x n, y n prime is y dash of x n. So, we get y n plus 1. So, these are the single step methods. Okay. So, now we would like to learn a particular method to solve IVPs, and this particular method is a single step method. Okay. So, what is that? It is very popularly known method, Taylor series method. Okay. So, we consider the IVP dy by dx equals to f of x y, y of x0 equals to y0, x belongs to x naught b. Okay. Now, when we say Taylor series, definitely we are going to use Taylor series expansion of the solution about some point. But before we do that, it would be better to know the assumptions under which Taylor series expansion is possible. Okay. So, I would like to write down the assumption. So, what is the assumption? So, the differential equation, which equation? Say the differential equation, this is 1. Okay. So, the differential equation 1, okay, has a unique solution y of x on x0 b and y of x has continuous partial derivatives of order say p plus 1 on so this is the assumption. What is that? The differential equation 1 has a unique solution y of x on x0 b, and essentially this is a existence and uniqueness theorem, and y of x has continuous partial derivatives of order say p plus 1 on this interval. So, then the solution y of x of 1, okay, can be expanded in a Taylor series, okay, about any point say x equals to x naught as follows. Okay. So, we will write down the Taylor series about x equals to x naught. So, it is given by into y dash of x naught plus factorial 2 y double of x naught plus so on plus p So, I switched over from this notation to this notation. So, please try to follow y1, y2 and then p. So, it is customary to put it in a parenthesis. Okay. This plus where this is, since we are expanding around x0, okay, within this. Okay. So, this let us call 2. So, in case we are expanding around x n, then zeta n varies x n to x. Okay. So, now this is a standard Taylor series expansion about x equals to x naught. Okay. So, now definitely when we use Taylor series expansion to compute a solution at a particular point, we have a lot of restrictions. What are the restrictions? The first restriction is how long we consider, how long we take the terms into account, like 5 terms, 10 terms, 20 terms. So, that means we have to consider the number of terms into account. Naturally, one would guess easily that the accuracy of your method has direct consequence in terms of the number of terms. Okay. So, let us see the last term, we have written it in a very specific form, because we have not written in terms of x 0, rather we have put it as zeta n, where zeta n lies within some interval. And now, this last term has a particular name, and then it has a vital role. Okay. So, let us see what is that. So, this is the remainder term, okay, R n. So, this is the remainder term. Okay. So, if we generalize y of x n plus 1, y of x n, and x h y dash of x n p plus R n. So, what is the notation we are adopting now? Earlier we have written, if you recall, we have written x minus x 0, x minus x 0, so on. Okay. So, now if you need at a particular point x 1, y of x 1 is y of x 0, x 1 minus x 0, y dash of x 0 plus x 1 minus x 0 square by factorial 2 y double of x 0 and x 1 minus x 0 power p factorial y p of x 0 plus the remainder. Okay. So, strictly speaking, this should be R 1, because we are expanding it. So, what is x 1 minus x 0? This is h, okay, the step size. So, therefore, x n plus 1 minus x n is our h. Okay. So, what I just have written is at x n plus 1, the Taylor series expansion at x n plus 1. So, this is the Taylor series expansion at x n plus 1, y of x n plus h y dash of x n plus h square by 2 factorial this and the remainder term. Okay. Right. Now, who is going to supply us the higher order derivatives? You see, suppose somebody would like to use Taylor series expansion up to 5 terms. So, then 5 terms means 1, 2, 3, 4 will be h cube, 5 will be h 4. That means the derivatives of y 5 are required. So, who is going to give us? It is the initial value problem which is going to give us. Okay. So, the remark here is the higher order derivatives. So, the higher order derivatives. So, these are the higher order derivatives. Okay. Are to be computed from the IVP. Okay. But how do we compute? If you look at it, your IVP is y dash equals to f of x y. So, we require higher order derivatives means under assumption. What is assumption? See, higher order. So, for example, y2 will be first derivative of f, right. So, y3 will be second derivative of f. So, we require higher order derivatives of y, which means we require higher order derivatives of f. Okay. So, now to have that, what is assumption? The assumption is f of x y is differentiable as many times as we require. So, these are the two assumptions. The first assumption is the higher order derivatives are to be computed from the initial value problem. I mean, this is not an assumption, this is a the process, but for that, what is assumption required? F of x y is differentiable as many times as we require. Okay. So, now let us try to compute. So, y dash of x n is f of x n y n, right. So, now we need, so in shorthand notation it is this. Now, we require y double. So, this is df by dx. So, this now we compute using chain rule, dou f by dou x plus dou f by dou y into dy by dx. But what is dy by dx? Yes, you are true, dy by dx is f. So, it is f, okay, right. So, we need y double of x n, this will be dou f by dou x plus f dou f by dou y at the point x n y n. Similarly, all other higher order terms can be computed. Okay. So, now with this, let us see what happens to our Taylor series. It is y of x n plus 1 x n plus h, okay, plus h square by factorial 2 dou f by dou x plus f dou f by dou y at x n y n plus the higher order terms h p factorial f p minus 1 plus, so the remainder I would like to introduce a term like this. Okay. So, this expression I am calling TS, that is Taylor series, okay, where epsilon p plus 1 equals hp plus 1 okay. So, this is the residual means the error. So, quick remarks, observe this term carefully, the derivative is p minus 1 h power p minus 1. Why is that? Because actually it should have been h power p yp, but yp is nothing but fp minus 1. Okay. So, this is the residual. So, what do you mean by residual? It is the error. Okay. Of course, I have not defined formally what is the error. So, we will definitely define. Okay. So, in what way we are going to define this error? Yes, as I mentioned, somebody is doing up to 3 terms, that means considering Taylor series up to 3 terms, and somebody else considering terms up to 10 terms, somebody 50 terms. So, we expect there will be a difference with the solutions. Okay. So, why is that? Definitely, see, you considered only 3 terms, other person considered 50 terms, another person considered 100 terms. So, the added terms should definitely refine your solution, so that it is more accurate compared to the solution which is obtained with only 3 terms, right. So, when you are considering, let us say 25 terms of your Taylor series, then what are we doing? We are forced to neglect the terms from 26 onwards, right. So, you expect that your solution is accurate up to that level. What is that level? Up to 25 terms, 26 and onwards we have neglected. So, if at all there is a deviation in your solution with the true solution, you expect that the deviation's contribution is from 26th term onwards. Okay. Suppose somebody considers 50 terms, then the deviation from the exact solution will be from 51st onwards, right. So, we are going to define this residual and discuss about it in a more rigorous way. Okay. So, that means if somebody says, okay, I do not mind my solution is if it is accurate only up to 1 decimal, I do not bother. So, then how many terms we can consider and keep quiet, right. So, we will be interested in, because somebody is asking you to have accuracy of only 1 decimal. So, why do you bother to compute 100 terms, 200 terms? It is not required, right. So, similarly, somebody would say with this step size, if you consider this many terms, then what will be the accuracy. So, these kind of trade offs, various trade offs. What are the trade offs between? If you know the error, means if you know up to this accuracy I need the solution. So, that is one quantity, the number of terms another quantity, then the step size is another quantity. So, there is a kind of a trade off among these quantities. Okay. So, let us have a careful look. Okay. So, remarks 1. Okay. If epsilon is a pre assigned number, then mod epsilon p plus 1 is less than C. This is the condition on the error, means if epsilon is pre-assigned, we expect that you must continue up to this condition, that is your residual must be less than epsilon. Okay. Then if h is given, the step size, okay, p can be calculated if p is given, h can be calculated theoretically, okay, theoretically, right, provided we replace by why is this? If you look at your epsilon p plus 1, it is h power p plus 1 by p plus 1 factorial and y p plus 1 of zeta n. So, this is h p plus 1 p plus 1 factorial f p of zeta n y n. Okay. So, this is our residual. So, now this residual is less than a pre-assigned number. Okay. So, mod of less than epsilon pre-assigned. Okay. So, if h is known, f is in our hand. So, we have to take the maximum of this and epsilon is known. So, we should compute p. Suppose p is known and epsilon is of course known, then we should be able to compute h theoretically. Okay. So, this is the trade off essentially. So, that means if the error is in your hand, means if you know up to this accuracy I need the solution, okay, and what are the other left out parameters? The step size h and the number of terms. Okay. So, you have to play with these two. The more number of terms, you expect more accuracy. Same time, if you jump, okay, so you are taken at one grid point, then with a large step size you are jumping, then one would expect less accurate solutions. So, this trade off is very much important. Okay. So, when we come across an example, specific example, we will discuss how to do this. Okay. So, now what is the process involved in Taylor series? Okay. So, let us define h times f of x n y n, okay, then y n 1 y n p minus 1 h as y dash y double y p. Okay. So, this is nothing but the right hand side of Taylor series, but for one term. So, if we define like this, then what was the number we have given? T s. Then T s become y n plus 1 equals y n plus h f. Okay. So, where we need y, we need all the quantities. So, it is n is 0, 1, say some n h minus 1. So, this is the corresponding single step processor. Okay. So, we believe that now Taylor series method is a single step method. As you can see, it will ask only one past value. However, higher order derivatives. So, we are not denying that. So, that has to do with the number of terms. Okay. Whereas, all the values, whether it is first derivative, second derivative or 50th derivative, all the terms are expected only at one past point. So, that is the motivation for single step method. Okay. So, therefore, we believe that Taylor series method is a single step method. Okay. So, before we discuss more about the error, so let us look at one specific example and see how do we compute the solution using Taylor series method. Okay. So, the example, say solve y dash is 3x y square and y of 0 is minus 1. Okay. To compute y of 0.2, okay, using Taylor's series, okay, Taylor series with h equals to 0.1, okay, then consider only first 3 terms of the Taylor series. So, suppose this is an example. So, what it says, for this ODE, this is the initial condition, we compute y of 0.2 using Taylor series with step size 0.1. Now, what is remaining? The number of terms. So, consider only first 3 terms of the Taylor series. Okay. So, let us briefly look at the solution. So, since it is suggesting to use only first 3 terms, okay. So, let us look at the Taylor series. So, the Taylor series is given by y n plus 1 is y n plus h factorial 2. This is our Taylor series, first 3 terms 1, 2, 3. Okay. Now, let us identify what is known data from there, from the problem. So, the known data is f. This is our f of x y equals 3x plus y square. Okay. and what else is known? X0, X0 is 0. Okay. Then what is known? Step size 0.1. Okay. So, now we need to compute y at 0.2. So, what is required? See, with h is 0.1, with x0 is 0, what is x1? X0 plus h. So, that is, so this suggests that our x2 is 0.2. That means we need to compute the solution at y of 0.1 and y of 0.2. So, that means we have to solve for y of 0.1, y of 0.2. Okay. So, we have to solve. So, let us so in order to solve, what do we require? We require to compute this term and this term, the rest in hand. So, y dash and y double dash you have to compute. So, let us do that. Okay. So, y dash is also in hand f of x y, which is given by 3x plus y square. Y double is 3. So, we can do using the formula, because general expression I have computed, but since we have a particular case in hand, I would like to do the chain rule directly here. So, y double is derivative of this with respect to x. So, 3 plus 2y into y dash. Okay. So, this is 3 plus 2y, y dash is 3x plus. Okay. So, now consider the case n equals to 0. So, then if n equals to 0 in this Taylor series, y1 is y0 plus h y0 prime plus h square by factorial 2 y0 double prime, right. So, let us write down y1 is y0 h y0 prime h square by factorial 2 y0 double prime. So, we have y dash and y double. So, now we require y. So, y0 is -1, y0 prime is y dashed of x0, which is y dashed of 0, which is f of x0 y0, which is f of 0 y0 is -1. So, this is 3 times 0 plus -1 square, this is 1. Okay. Right. Then y0 double. So, you can do it. So, this is the expression in hand. So, directly we can substitute. So, I do not want to do the algebra here, this is just for clarity. So, now directly 3 plus 2 into y0 is -1, 3 into x0 is 0 plus -1 square. Okay. So, this term is 0, this is 1. So, 3 minus 2, this is 1. Okay. So, maybe I have taken an example where the calculations are simplified. Okay. So, we have the data required in hand is this together with this, this together. So, minus 1 1 1 1. Okay. So, now we would like to substitute in star. Okay. So, we do it. So, y 1 is y of 0.1. So, that is y 0 plus h. So, this is y 0 is minus 1 plus h is 0.1 and y 0 prime is 1 plus h factorial 2 is 2, y 0 is 1. So, this is minus 1 plus point not 5. Okay. So, this is minus. So, this is our y 1. Okay. So, this is corresponding to n equal to 0. So, now let us take n equals to 1. So, if n equals to 1, then what do we need? Y 2 is y 1 plus h y 1 prime h square by 2 factorial y 1 double prime. Okay. So, we have to compute now y 1 prime y 1 double prime at x 1. So, y 1 prime is f of x 1 y 1. So, this is 3 x 1. So, x 0 is 0, h is 0.1. So, x 1 is 0 plus 0.1. So, therefore, and y 1 just now we have computed. So, therefore, okay. So, this one can simplify. Okay, we get this, right. So, now next quantity we have to compute this y 1 double. Okay. So, y 1 double is 3 plus 2 y 1 3 x 1 plus y 1 square. So, this is 3 plus 2 into minus 0.895, 3 into 0.1 plus minus 0.895 square. So, this is 3 so, let us give this minus here. So, this is 1.401 times. So, let us, you can also try, So, this is of course, some value we get it. So, this is exactly y 1 prime, right. So, we have it. So, this is exactly 1.1010. So, this is 1.401 into 0.1010. So, this is final, we get something like this 1.4574. Okay. So, y 1 double, right. So, now so once we get this, we have the solution in hand. So, it is a straight substitution. y2 equals y of 0.2 equals y1 is minus 0.895 plus h into y1 prime. Just now we got 1.1010 plus h square by 2 1.4574. Okay. So, this one can compute. Okay. So, we get some value. So, y1 is y of 0.1 and y2 is y of 0.2. So, you can compute at higher grid points. Okay. So, you can, but remember we have used only the first 3 terms only, right. So, if somebody would like to try further, so there will be slight modification in the values what we have obtained. So, now quick remark here is, if you see while computing y1 we would have rounded off. For example, there is a 0.1 square is there. So, we would have rounded it to some accuracy and then we have put down that. Then further y1 has been used to compute y2. So, we again cut down to some terms and then put down. So, every time we cut down. So, one kind of error is the number of terms. Okay, the number of terms we are throwing after a certain level. So, the other is at each computation you are throwing some digits and using that as information to compute further values. So, these are named with a specific terminology, but of course, they are the errors. So, the first one, that is neglecting after certain number of terms, is also termed as a kind of error. Then neglecting few digits and then using that information further is also termed as a kind of error. So, the more technical terms, exact technical terms I would define little later. Okay. So, now let us look at the thrown out part. In this example, we have calculated using first 3 terms. That means, we have thrown from 4th term onwards. Okay. So, let us look at this 4th term so that we understand what is happening. Okay. So, let us look at the 4th term. So, what is that? So, our p was 2 because h square. So, this is p plus 1. So, this is epsilon 2 plus 1, this is epsilon 3, this is so let us say we are considering this at first point. Okay. So, that means while computing 0.1. in this. Okay. So, what is this? And y3 is f2, y3 is f2. Okay. y3 is f2, right, f2 of this. Okay. So, for this example, let us look at this quantity. We have only f1 in hand. So, what is that? f1 is 3 plus 2y 3x plus y square. Okay. So, now f2 3 plus 2y prime, that is 2 3x plus y square I am keeping, y prime is f. So, that is 3x plus y square plus 2y into 3 plus 2y y prime. Okay. Right. So, let us compute this f2 at zeta 0 y 0. So, y 0 is for this problem y 0 we have considered is minus 1. So, if we 3 plus 2 into x 0 is 0, y 0 is minus 1. So, we get 1. So, this we get 1 plus y 0 is minus 1. So, minus 2 and here 3 plus this is minus 2 and I am sorry. So, this is not correct, because x 0 3 plus 2 x zeta 0 plus 1 into 3 zeta 0 plus 1 minus 1 3 plus minus 2 y this is y prime. So, this for the time being I am putting, next line I can simplify 3 plus 2 into 3 zeta plus 1 square minus 2 into 3 minus 2 y prime is 3 zeta 0 plus 2. Okay. So, essentially this will be some function of zeta 0. Okay. This will be some function of zeta 0. Okay. So, now this zeta 0 is varying in this interval. So, let us say you are computing zeta 0. So, 0 less than zeta 0, let us say 0.1 you are computing next solution, it is within this interval. So, now we have to analyze. Okay. So, how do we analyze? Naturally, we have to look for the maximum. Okay. So, mod epsilon equals is less than or equals to maximum of zeta 0 in the interval 0 to 0.1 of z of this. Okay. So, this value if we compute, then one can say y of 0.1 is accurate up to. So, this we get some say epsilon, say we are getting this as some 3.54 into 10 power minus 4. This is a say, not for this problem, because it is a bit lengthy calculation. So, I am just showing you for example. So, that means y of 0.1 is accurate up to 3.54 into 10 power minus 4. Okay. So, this is the residual. So, I have not yet mentioned what is the error, different technical names of various errors. What kind of errors? I told you the number of terms, there is one name, and then we cut the digits, there is another name. Okay. So, we formally learn in the coming lectures. Okay. So, this is how the Taylor series method would give you approximate solution. So, the assumptions are first of all you would be able to compute higher order derivatives as many times as possible. Then one can get approximate solution up to some accuracy, which depends on the number of terms one would consider. Okay. Thank you.